Welcome to the start of Unit 3 and our first topic, the power rule. At this point, we have now finished units on both limits and getting into the concept of derivatives. And what this unit and the upcoming units are all going to serve to do is to lead us into applications of derivatives and methods for analyzing, methods for making the math easier when we deal with derivatives. So very first thing, let's get back to some notation regarding derivatives. Recall that we have several main ways to notate a derivative. We have f prime for a function f of x, f prime of x to give a function notation, y prime when dealing with an equation y in terms of another variable, could be a function, might not be, and dy dx, talking about a change in y or our dependent variable over a change in x. And that's the one that most closely resembles slope, which again, that is the whole idea for the derivative, is the slope of a tangent line and the instantaneous rate of change. So the first thing that we are going to look at in this section is one of our first methods for analyzing, like I mentioned, and this method will allow us to differentiate anything of the form x to the n, where we have a function of x raised to a constant power. And the rule for dealing with derivatives of this form is to take our exponent and move it to the front to become a coefficient, and multiply that by x to the n minus 1. So our exponent gets lessened by 1, and the old exponent becomes a coefficient. If you'd like a proof of this concept, the video for that can be found on my YouTube channel. But if you're not really too concerned about proofs, then just make sure that we memorize this rule so that we can utilize it going forward. And why this rule will be helpful is it allows us to then describe the derivative and therefore the instantaneous rate of change for anything that's written as a polynomial or powers of x. So for example, find the derivative of this following function. F of x equals 3x to the 7th minus 4x to the 5th minus 1/3 x to the 3rd plus x squared minus 3x plus 7. Very long function, but all we have to think about is it's really just 6 individual parts that all follow this one rule. And so to get the derivative of that function, something that will describe the slope, the instantaneous rate of change anywhere, well, on the first term, that 7 will be multiplied to the front, and 3 times 7 will give me 21. And the exponent will decrease by 1 and become a 6. On the second term, the 5 will get multiplied to the front. Negative 4 times 5 is negative 20, and x to the 1 less, x to the 4th. 3 times 1/3, well, that's just going to be a 1, and we're going to get negative x to the second power. It goes down by 1. Plus, this 2 comes out in front. It goes down to x to the first power, or just x. Now this one gets a little bit trickier. This is an exponent of 1 that when multiplied to the front becomes a negative 3. But then we get x to the 0, which is really just 1, and we don't need to worry about writing that. And finally, any constants, those are going to have a derivative equal to 0, and they're going to go away. And this will be our final derivative function. And if you need to, think about the constant functions in this way. It is a horizontal line. Horizontal always has a slope of 0. So if the slope is always 0, it should follow that the derivative is always 0. And let's try one more. Y equals 2x to the negative 3 plus 4x plus pi. Keep in mind, this power rule works for any power that has a constant value. So even 2x to the negative 3, it's a negative power, but we can still deal with that. This 4x is an x to the 1. So let's get dy dx for this function. Dy dx equals negative 3 times the 2 makes a negative 6. X to the, and negative 3 minus 1 is negative 4. 1 times the 4 is going to be a plus 4. That becomes x to the 0, which means it's gone. And pi is a constant, so its derivative is 0. And there is my final answer. So again, all this rule serves to do is allow us to quickly evaluate the derivative for anything that can be written as a power of x. So even when I look to these examples, I have y equals the cube root of x to the 7. That is just x to the 7/3 power. Minus square root of x, that is x to the 1/2, and plus 2 times the 5th root of x squared is 2x to the 2/5. It'd be really useful if we make sure that we recall, review, practice if we need to, changing radicals into fractional exponents and switching back. Because now I can take this derivative quite easily. Dy dx, well, this exponent moves out to the front. I'll get 7/3 x, and then 7/3 minus 1, or minus 3/3, is going to be 4/3, minus 1/2, x to the 1/2 minus 1 is negative 1/2, plus 2/5 times 2 is 4/5, x to the 2/5 minus 1, negative 3/2. I would say don't even worry about right now changing those back into radicals, worrying about the negative exponents. It's just us making sure we are able to go through this process of applying this new power rule. Moving on, g of x equals, now all these are fractions, so I'm going to rewrite them as negative exponents. 1 over x is x to the negative 1. 4 over x squared is 4x to the negative 2. Now this term down here gets a little bit tricky, but it's really going to be 1 over 3x quantity squared, 9x squared. So that's going to be minus 1/9 x to the negative 2. And now I can take that derivative quite easily. The negative 1 moves out in front. I'll get negative x to the negative 2. Negative 2 times 4 is negative 8, x to the negative 3, and negative 2 times this negative 1/9 is plus 2/9 x to the negative 3. And lastly, this one might not look like you can do this with the power rule, but you have to think about how we can simplify fractions. And keep in mind, I have 3 terms in the numerator divided by 1 term in the denominator. Well, I can just divide each of those terms by 2x and rewrite this as negative 16x squared divided by 2x is negative 8x. 5x divided by 2x is plus 5 over 2. And negative 1 divided by 2x is going to be negative 1/2 x to the negative 1. And differentiating all 3 terms, derivative of negative 8x is negative 8. Derivative of this constant 5/2 is going to be 0. And derivative of the negative 1/2 x to the negative 1, that would be a plus 1/2 x to the negative 2. Using the power rule, now again, anything that can be written as powers of x, we can now actually find derivatives at values of x. So for instance, f of x equals 1/2 x to the 4th minus 4x to the negative 2 plus e. My goal is to evaluate f prime of 3. Well, first I need f prime of x. Well, 1/2 x to the 4th, 4 times 1/2 is 2. Goes down by 1, x cubed. Negative 2 times negative 4 is plus 8 x to the negative 3. And this is a constant, so it will go away. Its derivative will be 0. And f prime of 3 will be 2 times 3 cubed plus 8 times 3 to the negative 3. Now when you go to evaluate this, this is where you might want to switch back into having a positive power. Use the reciprocal of 3 to the negative 3 and make it 8 over 3 to the 3rd power. So I'm going to say use the calculator and get 54.296. Let's look at the one right next to it. So y equals 1 over square root of x plus 4x. Well, I know that that square root of x is an x to the 1/2, and being in the denominator, this will be x to the negative 1/2 plus 4x. So dy dx will be negative 1/2 x to the subtracting 1, negative 3/2, plus derivative of 4x, which is 4. To go ahead and change this back into a positive exponent. And now I can go ahead and evaluate this at x equals 4. Negative 1 over 2 times 4 to the 3/2 plus 4, which will be equal to negative 1 over 16 plus 4, or 3.938. And looking to the bottom, we're going to look at what are known as higher order derivatives. So being able to not only find the derivative of a function, but being able to find derivatives beyond that. And what I mean is, let's look at this lead function over here, f of x equals x to the 7th minus 2x to the 4th plus 5x squared minus 3x plus 9. Well, taking f prime, taking the derivative of this function will give me 7x to the 6th minus 8x to the 3rd plus 10x minus 3, and again that 9 goes away. But we're actually able to take the derivative of a function as many times as we want to, and we're going to start to see what that is actually going to represent to us in real-world application. So I can start from f prime and go to f double prime. That just means take the derivative one more time. And derivative of 7x to the 6th will be 42x to the 5th. Negative 8x to the 3rd will be negative 24x squared. Derivative of 10x will be plus 10, and the negative 3 goes away. And I can keep moving down this chain. Derivative of 42x to the 5th, well, that will be 210x to the 4th minus 48x. The 10 will go away, and I can keep going as far as I want to. Now, what you'll notice is, especially for something like a polynomial, eventually, if you run the derivative enough times, this will turn into the number 0. But as long as I still have powers of x left, I can keep taking further and further derivatives. And now we can finish up with the problem on the right side. We have y equals square root of x plus x to the negative 2. The first thing I'm going to do when I can is rewrite my problem all as powers of x. So square root of x becomes x to the 1/2. This x to the negative 2 is already written as a power of x. And so the derivative dy dx will equal 1/2 x to the negative 1/2 minus 2x to the negative 3. Now what this is asking, this d squared y dx squared is the same as that f double prime of x. And the phrase we're going to have for that is second derivative. So just realize that these two notations are exactly the same. Differentiating once again, the negative 1/2 times the 1/2 will be a negative 1/4. X to the negative 3/2. Negative 3 times the negative 2 will be a plus 6. X to the negative 4.
This section is a return to something we talked about back in Unit 2, finding the value for a derivative on the calculator. Make sure that you have your calculator handy, and we'll go back over the steps for this one more time. You press Math, and then 8, and it brings up this formation here on the TI-84. It might look slightly different depending on what calculator you are using, but if you have any questions on how to use this tool, we just might need to figure out what the exact procedure is for using your calculator. But for this first example, f of x equals 1/2 x times the square root of 2x minus 1, we're going to say that we're differentiating with respect to x, and then type in our function. The piece at the end, the x equals, is where we want to evaluate the derivative. So for f prime of 4, I want to set x equal to 4, and we'll get 2.079. And so what I'd like you to do is go ahead, pause the video, and see if you can't evaluate the other numerical derivatives that are at the top of this page. Keep in mind when you go to do f prime of e, you should have x equals, and on most TIs you're going to have to do e to the first power in order to get that. Right? E is set up down here if you press second natural log. So doing e to the 1 will allow you to set x equal to e. And hint for your f of theta function, if you're confused on how to get cosecant in there, you could always set that up as 1 over sine of theta, or switching everything on the calculator to x, 1 over sine of x. So go ahead and try to evaluate the rest of them. When you're set, unpause the video to check your answers with mine. And so checking your answers, f prime of e for the f of x function on the left should have been 1.698. On the right, dealing with this f of theta, f prime of pi, notice you're going to have negative 1,000,000.167. That's because the calculator isn't quite sure how to deal with the result it gets, that very negative number, which means we're dealing with a very vertical tangent. You can say it's going to negative infinity, or you can say that this does not exist. Once you get to a certain point and it's straight up and down, the slope will be undefined, and so will the derivative. But f prime of pi over 2 is definitely equal to the number of 0.
Moving on to some more applications though, let's remind ourselves of what the derivative means to us and start bringing that together with what we've learned about this power rule for functions. Derivative means slope at a point. So given y equals 1/2 x to the 4th minus x plus 2, find the slope at x equals 2. Well, first I do my derivative. dy dx equals, well, 1/2 times 4 will be 2x to the 3rd minus derivative of this negative 1x will be minus 1, derivative of 2 will be 0, and evaluating that at x equals 2, we'll get 2 times 2 to the 3rd minus 1, which will be 15. Derivative also means slope of the tangent line. So we've seen this problem a couple times now. Write the equation of the line tangent to this same function at x equals 2. Generally, we'd want to get the derivative, but this is already a function that we've worked with. We would also want to get the derivative value in order to figure out the tangent slope, which we've also already done. Now recall, in order to make the tangent line, not only do I need my x value and my slope, I would also need my y value, specifically the y value when x equaled 2, and that would equal 8. In my equation, putting this into point slope form, would be y minus 8 equals my slope of 15 times x minus my x value of 2. Another thing that we learned about the derivative is that it also stands for the instantaneous rate of change. So what is the instantaneous rate of change at 3 seconds for this s of t function? Get used to seeing t represent time. So if this is our s of t function, the instantaneous rate of change is going to come from s prime of t. This is all power rule right here. So 2 times negative 4.9 is negative 9.8, t to the first power, plus 40, that would become t to the 0, so that would go away. The derivative of the 6 will be 0, and we're just being asked to evaluate s prime of 3. So negative 9.8 times 3 plus 40, and s prime of 3 would equal a positive 10.6. And so the last thing that we're going to look at in terms of concepts and any sort of application that we want to do in this lesson is the idea of the normal line. And so remember, everything we've talked about has been about tangent lines. Well, a normal line is just talking about a line perpendicular at a point. So normal, when you read that word, is a fancy word for perpendicular. But the process would be the exact same as what we ran through on the tangent line. Very first thing, I want my normal line at x equals 3. Well, first I'm going to need my y value. So I'm going to be doing f of 3, which will be 3 cubed minus 4/3 squared plus 3 plus 3. And f of 3, my y value will be -3. And the last thing that I'm going to need is my derivative value at 3. Now the derivative of this function is going to be 3x squared minus 8x plus 1. And f prime of 3 is going to be 4. But remember, that is the tangent slope. In order to get the normal slope, what we have to remember from previous years, a little bit of review into our algebra knowledge, is in order to get a perpendicular slope, I take any slope that I may have, like this 4, and I do the opposite reciprocal. So if my tangent slope was 4, the perpendicular to that tangent would be -1/4. And I can now easily write the equation of this normal line. It would be y minus my y value, which was -3, so plus 3, equals the slope, -1/4, times x minus my x value. And so I'm going normal at 3, -3. Imagine that this is my tangent line right here. The perpendicular, or the normal line, will be the line going through that point with a slope of -1/4. So moving backwards, we'll go up 1 and 4 to the left. And when I connect those, what I now have is a line that at that moment in time is perpendicular to my curve. Now, one question you might ask yourself is, why would that ever be useful? And in general, not too much. The one spot that you would see this is in physics. And we're going to be dealing a lot more with physics going forward, so we might have a chance to see an application of normal, or if you take a physics course, you will definitely see this concept pop up. Whenever you're standing on a flat surface, there are always two forces acting upon you. The force of gravity pushing you down, and what is known as the normal force of the ground or floor pushing back to prevent you from going through the floor. And, as you can see from this diagram, the normal force is perpendicular to the ground. So that's really the main application of what you'd see for this concept of normal. So to wrap up what we've had in this lesson, the main takeaway was this power rule, dealing with differentiating any function that is a constant power of x. Along the way, we ran into the idea that the derivative of any constant is equal to 0. And again, just think about the slope of any constant horizontal line. Two other rules that we've run into and kind of took for granted, the constant multiple rule, such as what we might see when differentiating something like 2x, where if I have a constant times some function of x, my derivative will be c times the derivative of that function of x. So derivative of 2x was 2 times derivative of x, which was just 1, and it went away. And we also took for granted this sum or difference rule that says the derivative of any two functions, u and v, that are functions of x, if it's u plus v or u minus v, all this is saying is I can take the derivative of each of those functions individually, as long as they are a sum or a difference. So now you've gotten through one of the most powerful tools that we are going to use to evaluate derivatives. Please make sure that you review and summarize your notes, and when you're ready to move on, the following sections will bring up some more rules that are going to help us with our derivatives, along with exposing you to further applications of the concept of the derivative. Thank you for watching.